This is Chapter 6 from AS Applied Maths Statistics. We're looking to introduce statistical distributions today. After completing this section, you should be able to understand and use simple discrete probability distributions, including the discrete uniform distribution. A random variable is a variable whose value depends on the outcome of a random experiment. What we mean by that is that the outcome is not known until the experiment has been carried out. So for example, we may have a random experiment which involves rolling a dice 3 times. A random variable could be the number of 4s obtained. It's just important to note that when we are looking at random variables, these are always denoted by capital letters. The sample space, denoted by S, is the set of all possible outcomes that a random variable can take. So for example, if we looked at flipping a coin, the sample space would include a head and a tail. A random variable is called discrete if it has a finite or countable number of possible values. So for example, the number of students who are late to my class on a given day. As a student is either late or not late, this variable can only take integer values up to and including the total number of students in the class and can therefore be described as discrete. A probability distribution is represented using a table, and it fully describes the probability of any outcome in the sample space. Example 6.1.1, write down the probability distribution of x, where x is the score when a fair dice is rolled. As mentioned, the probability distribution should be represented in a table, the first row of which considers the particular values our random variable can take. In this case, we are considering the score when a dice is rolled, and so our possible values are just 1, 2, 3, 4, 5 and 6. Please just note the notation used here. We have our random variable, which is always denoted by a capital letter, but when considering the particular values our random variable can take, these are always denoted using the equivalent lowercase letter. Next, we consider the probability that the random variable takes each particular value. So for example, the probability that we score a 1, 2, 3, etc. This should just be denoted in your table as the probability that your random variable, so your capital, is equal to all possible values, so your lowercase equivalent. Now, because we are given a fair dice, we know that we have an equal chance of scoring each number, and therefore all of our probabilities are just equal to a sixth. If this is something that you are unsure of, please can you go back and recap Chapter 5 on probability in your own time. If we wanted to represent the above distribution on a diagram, we would plot our probabilities on the y-axis and our possible values on the x-axis. So we'd be left with something similar to below. The probability mass function is just another way of describing the probability of any outcome in the sample space. So it's very similar to your probability distribution, it just takes a slightly different form. So here we would specify the probability that our random variable takes each possible value of x was equal to, you would use a large curly bracket. Here we would then just denote our probabilities, and then we would specify for which values of x. In this particular example, we know that our probability is equal to a 6 for all values of x, so we can just write our probability mass function as follows. So we've got a 6 for 1 through to 6. If it wasn't the case that you had the same probability for all your values, you would just list your next probability and for which values of x underneath. It's also really good practice to just denote that it's 0 in every other case, so 0 otherwise, and that is your probability mass function. So all of these representations show the probability that the random variable takes any given value in its sample space. So in this example, we're looking at the score when a fair dice is rolled and the associated probabilities. When all of the probabilities are the same, so for example in this case where we have a 6 for each outcome, the distribution is known as a discrete uniform distribution. Please can everybody pause the video now and attempt example 6.1.2. Okay, so I hope everybody attempted this question. If you do have a different coloured pen, it's really good revision technique to mark your own work as we go through the solution, because it helps you to identify the areas which you may need to revisit. Given an experiment where two fair coins are tossed, we are told that the number of heads x is counted. X is then our random variable. The first part of this question asks us to find the sample space. So these were recapped in the probability chapter, so we should be familiar with the fact that we denote the sample space by the capital letter S. We then use curly brackets when we're considering set notation, and we just need to list all the possible outcomes for this experiment. So if we were to go ahead and toss a coin 2 times, we could get a head followed by a head followed by a tail followed by a head, or 2 tails. And it's just important to highlight that we need both head tail and tail head. So although in both of these examples we are getting 1 head and 1 tail, when we're conducting the experiment we are achieving those in a different order, so both outcomes need to be listed in your sample space. Part B then asks us to find the probability distribution. So remember, this is a summary of probabilities for each outcome in the sample space, so we can use part A to help us. In terms of the possible values for our random variable, we could either have 0, 1 or 2 heads because we're looking at throwing a coin 2 times. Then moving on to our probabilities, if we have 0 heads, then this has to be the outcome that we obtain 2 tails. So the probability there is 1/4, and you should be able to see that easily from your sample space. In terms of 1 head, then we've got 2 possible options here, because we could obtain a tail and a head, or we could also have a head and then a tail, and in both situations we have 1 head, so that probability simplifies down to a half. And then finally we have the outcome where we have 2 heads, in which case we have the probability of a quarter again. So finally, part C asks us to write down the probability mass function. These should be the probabilities that you found in part B, but just written in a slightly different format. It is important to note that the sum of the probabilities of all outcomes of an event should add up to 1. So this can be a really good sense check during an examination. If you take the sum of your probabilities, these should all add up to 1. Here we can see that is true and it holds. Questions may also be given during the exam where a probability or multiple probabilities are unknown, and you will be expected to use this key point to find your unknown values. So we're going to move on to an example like that one now. Example 6.1.3, a die has numbers 1, 2, 3 and 4 on its faces. The die is biased in such a way that the probability of the die landing on any number x is k/x, where k is a constant. Find the probability distribution for x, where x is the number the die lands on after a single roll, and we need to write x also as a probability mass function. So to begin this question, we know our random variable is the number the die lands on after a single roll. From here we can begin to formulate our probability distribution. So if we consider the possible values our random variable can take, the question indicates that these are 1, 2, 3 and 4, because they're the numbers on the die's faces. Then moving on to their associated probabilities, the question again highlights that the probability of the die landing on any number x is just k/x. So again, we can substitute our possible values of x in to find the following. So we would have k/1, k/2, k/3 and k/4. Now, since this is a probability distribution, we can use the fact that the sum of the probabilities of all outcomes of an event should add up to 1. So we're going to use the fact that the sum of our probabilities should equal 1. Just a tiny bit on notation, this is capital sigma. So by summing over our probabilities and equating them to 1, we should be able to create an equation involving k which then can be solved. So if everyone can now please pause the video and attempt to complete the rest of the question. So you'll need to find k, redefine your probability distribution and also define your probability mass function. So hopefully everybody has attempted to define both the probability distribution and the probability mass function. To quickly recap, we have taken the sum of the probabilities of all outcomes for this event and equated them to 1. This has allowed us to create an equation involving k which we can then solve. Here I have just multiplied by 12 and that's just because it's the lowest common multiple, so it's allowed me to remove the denominator. From here we should all find that k is equal to 12 over 25. This can then be substituted into both your probability distribution and your probability mass function, and we should have final answers in the following form. Please can everybody pause the video now and attempt the following example. Okay, so hopefully everybody managed to attempt example 6.1.4. Similarly to before, if you could mark your answer in a different coloured pen, that would prove really useful. To begin, we are asked to find the unknown value of A. Similarly to the previous example, we need to use the fact that the sum of the probabilities for all outcomes of an event do add up to 1. So this example is slightly easier as we have been given the probability distribution in the form of our table already. So here we can just sum over our probabilities, equate them to 1 before rearranging to find the value of A. Here we should find that A is 0.1 and I'm just going to add that to the probability distribution above, which should help us with the following questions. So part B, C and D all ask us to find probabilities. One of the advantages of having a probability distribution like this for a discrete random variable is that we can easily, by looking at the table, see individual outcomes and the probabilities associated with those. But we can also quickly calculate the probability that our random variable is greater than or less than a value, or even falls within a given range. And that's just by adding the probabilities up. So part B asks us to find the probability that x is between 2 and 4 inclusive, which we can just rewrite as the sum of the probabilities that x is equal to 2, plus the probability that x is equal to 3, and then finally the probability that x is also equal to 4. And that leaves us with our final answer of 0.75. So we don't particularly know in this case what our discrete random variable is, we just know that it's denoted by the letter x, but we do know that the probability that x takes the value 2, 3 or 4 is 0.75. So part C is very similar, and again I'm just going to consider the possible values of x that satisfy the condition given in part C. So here we can see that we would include the probability that x was equal to 4, that x was equal to 5 and that x was equal to 6, and that leaves us with a final answer of 0.4. So exactly the same for part D then, so we want the probability that x is less than 3.24, so I'm just going to consider all the possible values of x for which x is less than 3.24, and here using our probability distribution we can see that that's true when x is 3, 2 and 1. So I'm just going to add up the probabilities that I've just circled to find the probability that x is less than 3.24, and we're left with 0.6. Example 6.1.5. So again we've been given a discrete random variable, but in this case we've been given the probability mass function rather than the probability distribution. And similarly to the examples earlier, we need to find some probabilities, but before we do that we need to find an unknown value, in this case k. What I would say is if you are unsure of where to start, try rewriting your probability mass function as a probability distribution and try working from there. If everyone can then pause the video now and attempt this example, and then we'll run through it together. Example 6.1.5. So before we attempt part A, I am just going to rewrite the probability mass function as a probability distribution. You may have done the same, and if not, please don't worry, it's not a required step, but as mentioned earlier, summarising our information in a probability distribution can make it much easier to see individual outcomes and their associated probabilities. In terms of finding the probability distribution, if at first we consider the possible values of x, we can see here from our probability mass function that these are 0, 1, 2, 3 and 4, and we then need to look at the associated probabilities, knowing at this first stage that they will be in terms of k. So to do this, we just need to substitute each value of x into the relevant expression when we're looking at our probability mass function. So if we look at the probability that x is equal to 0 to begin with, we can see that we're looking at this first expression. So we've got k, 0 plus 2, which then simplifies to 2k. So we can pop that in our table. Moving on then, if we wanted the probability that x was equal to 1, in this example, we're looking at our second expression listed in the probability mass function. So again, we've got k, but this time we have 1 minus 1, which then simplifies to 0. We just then need to continue working through the possible values of x and substituting into the relevant expression. And we should see that we get 4k, 2k and 6k. So again, if you haven't completed this step, please don't worry. So then from here we can use that the sum of the probabilities of all outcomes of an event add up to 1. So this is where I was saying that it's not necessarily a requirement to have your probability distribution. You could formulate the following equation using your probability mass function, but it can make it just slightly easier to see. And once we've done that, we should all find that k is equal to 1 over 14. And I'm just going to pop those values into our probability distribution just to help us with part B and part C. So part B asks us to find the probability that x is greater than 0 but less than or equal to 2. So similarly to what we were looking at earlier, we need to consider all the values for x which satisfy this condition. So in this case we have when x is 1 and when x is 2, and we need to add those associated probabilities. In this case, the probability that x is 1 is just 0, so we are left with 4 over 14, which we can just simplify to 2/7. And then finally, part C asks us to find the probability that x is greater than or equal to 3. So again, considering the values of x which satisfy this condition, we need to add the probabilities where x is equal to 3 and where x is equal to 4. So once we've added those two probabilities and simplified, everyone should have 4 over 7.